But what if we did want to find that normal force? What if we wanted to look into it? Well, one of the very unique things about a torque problem is that you can choose your center of rotation. Instead of choosing this point right here and doing all the work as we did here, I could choose this point, right underneath the child of the green forces. In this case, how the sum of all torques changes. In this case, because I'm rotating around this point, all my radiuses are going to be measured with reference to this point. In addition, all the torques I find are going to be measured with reference to this point. So when I look at RF for the red one, get out my fingers, I point them along. R is here now. And again, we're going to treat these as 90, make our math easy for right now. This is my R of 2 meters, and it points up, so my thumb will end up pointing out the page. This one's going to be positive. The blue is still going to be negative in this case. But the green one is at the point I'm pivoting about. It's 0. So whatever value here is 0. Now, had I not done the previous problem first, I couldn't solve this. If I go a little farther, at this point, I don't know my tau, I don't know my Fn. I know my m and g, I can actually put those numbers in right now. But because I did the previous problem and already found that my net torque is 39.2, I can now solve for my normal force. An interesting follow-up to this is, what if I had chosen the blue point? What if I had measured everything from here? In this case, the problem setup doesn't change too much initially. The big difference in this case is when I go to do my vectors. In this case, my normal force will be negative. My blue will be 0 because my point of rotation is here. And my green will still be positive, but in this case, have a radius of 2 plus 1.8. Either way you do it, as long as you pick a point and stay consistent and pay attention to your right-hand rules, the math will work out. Go ahead, give this a try. Do either using the green as your rotation point or the blue as your rotation point. Go through the work, check it out. Do both if you really want to and see how they compare, and then check back after the pause. If you look at the bottom, before we even go through the math, you'll see that we get the same number, Fn equals 1323. This is really fascinating, that no matter how we set it up, as long as we're consistent, the math will bear out and give us the correct answer either way. There are many different ways to solve these problems all of a sudden, or more ways than you're typically used to. You get to choose your point. Regardless of how you do it, the math bears it out. Do be very careful that your radius is appropriate. If I'm measuring from the blue child, if I go back to my image really quick, the radius is the 1.8. Or if I'm measuring from the green child, that's 2 meters. So that normal force's distance will vary based on where you start from and how you go about it. So do be very careful about that. But if you did that everything right, the math bears it out. And you get the 1323 newtons. And that's not torque in a nutshell. Though there is a small complication that we haven't factored yet. In this problem, we didn't account for the weight of the seesaw, the mass of the seesaw, the force of gravity pulling down on the seesaw, which, in honesty, would be here. Now, if we use an approximation that says that the seesaw is massless, or effectively massless, this gets really simple. We can use the math we have. But in the real world, objects have mass. Even when you're standing on a board that's pivoting, it also has mass, and it will factor into the equation. Ultimately, we know that in this case, the normal force is going to be bigger than the force gravity because it has to hold everything up and it's causing rotation. The net force at this point isn't 0, so we know this is bigger. The 13 23 I found is actually how much bigger than the weight of the seesaw the normal force has to be. But how do we find the actual normal force? How do we find the actual weight of gravity? Because if I were to put this in an mg, I'd have two equations. And unlike previous worlds, this system of equations doesn't help us. That's the next question we'll have to answer, but that's a problem for another day. To summarize, torque is rotational force. It is equal to the moment of inertia times alpha, and the net torque will equal this, where you can add up all your individual torques. We can also find torque by multiplying the radius times the force perpendicular to the radius, or r times f sine theta, to calculate the torque. When we solve for the net torque, we can pick our center of rotation. Typically, we want to choose a center of rotation, such as here, that discounts as many forces that we don't know. In this case, we don't know the normal force or the weight of the seesaw, so we choose the point in the center to find the net torque. Once we've found the net torque, however, we can use it and go back and use different centers of rotation, such as under the green child or under the blue child, or if you really wanted to, somewhere in the middle of the beam, like here, and calculate all the other unknown forces. Typically, again, we don't want to choose somewhere in the middle. We want to choose somewhere where one of the forces are so they factor to zero and make our math and life easier. Anyways, thanks for watching. Have a good one.